Okay, so this is the first part of Unit 6 for us, which covers Chapter 15 in our textbooks on chemical equilibrium. One of the things I've been saying repeatedly throughout class to help you remember this is that equilibrium occurs when the reaction of the forward and the reverse reaction happen at the same rate. It does not mean that there's equal amounts. It just means they are happening at the same rate, the same speed, if you will. This image here shows you what happens when bromine, this is Br2 here in the image, is exposed to heat, or I'm sorry, not bromine, it says it right there, NO2. Okay, so NO2 goes between N2O4, and this is 2NO2. The reason why I said bromine is because bromine as a gas is also brown, like in this last picture. So what happens is when it is cold, it is in this colorless N2O4 form, if you will. And when it's heated or warmer, then it is in this brown NO2 form. It looks like that. This is actually a component of smog. That's why sometimes on hot days it looks worse. And so there's this idea of by changing the temperature, we can shift equilibriums and control what types of products and reactants we get and how much. And that's Le Châtelier's principle, which we're coming to. So, but back to this concept of just equilibrium in general. As a system approaches equilibrium, both the forward and reverse reactions are occurring. When they hit the same rate, they are equal. So it's really important to look at the axes here on the graph. You've got time on the x-axis and rate on the y-axis. So right here, where those lines join is when you are at equilibrium. So now they're happening at the exact same rate. Now, graphically, equilibrium can look kind of different here. So the reason why I said look at the axes is because this axis right here is concentration. So equilibrium does not mean you have equal amounts, okay? You can have different amounts of stuff. So like here, once equilibrium's been achieved, my NO2 and my N2O4 actually have different concentrations because the brown line and the blue line are at different heights. But notice the key point here is the lines have flattened out. The concentration is no longer changing. So that's another way to see equilibrium graphically. So an equilibrium graph with concentration can look like there. It could also look like this, where the lines never meet. And it could also look like the one on the last slide where they do join. Okay. So really there's three possibilities for, a concentration versus time graph. This graph will also work for pressure. In fact, as we'll see, pretty much anytime I say concentration, you can substitute the word pressure in there. So it gets the double arrows. Again, you should have seen these before. They look a little wonky. Chemists are lazy, so we don't write the other half of the arrow. You can, but like I said, most chemists don't write the full head to the arrow. They just stack them up. So I mentioned a few moments ago Le Châtelier's principle, and Le Châtelier was a French guy, and he essentially said that if you put a change on a system that's at equilibrium, if you put a stress on it, then the system is going to change in order to relieve that stress. So just like you, when you are under stress, okay, you're going to do something to relieve that stress. You're going to either get whatever's stressing you done or out of the way or something, or go work out, whatever you do to relieve stress, hang out with friends. In chemical systems, it's the same sort of idea. But here, in chemical systems, your three stresses are temperature, pressure, and concentration. Okay? So those are our three stresses, is temperature, pressure, and then concentration. And remember, concentration is square brackets. We're going to see that a lot there. So it's going to shift in response to those. So I'm going to skip that one here. So this is really important for industrial processes. One process you're going to see a lot here in the beginning is the Haber process. And the Haber process is the way we take nitrogen and hydrogen and turn it into ammonia. And industrially speaking, ammonia is really important because we use it for fertilizers for our crops. So ammonia doesn't occur in large amounts naturally, so we want to produce it in order to help our fertilizers. So if we are doing the Haber process here, if we add hydrogen to the system, that means we're going to use up more nitrogen and it's going to form more ammonia. So essentially, if I increase my reactants, it's going to shift the equilibrium to the right and I'm going to get more products. Okay. So here we can even see on a graph, I put in more hydrogen right there, so it caused that spike, and then all these things adjusted again. It used up more nitrogen to compensate for the extra hydrogen. Conversely, if I decrease my reactants, okay, let's say I take out some hydrogen or some nitrogen, then my equilibrium is going to shift to the left. And some of those products are going to be used up in order to make reactants. So if I remove something from the system, it's going to try and put it back. If I add something, it's going to try and compensate by using it up. So anyway, this is a picture of the diagram that they use for the Haber process. And you can see here, like right here is where they add in the nitrogen and the hydrogen. And then out here is where the ammonia comes out, the NH3, the desirable product. So it just keeps going and going and going. You can see here, you've got a catalyst and your unreacted nitrogen and hydrogen can be recycled and used again. But, you know, that's just some more background on it. So again, I'm changing pressure, and this diagram here is not really working. So if I'm changing pressure, the rule for changing pressure is looking at the number of moles. Okay, so I want to look at the number of moles in the reactants and the products. So if I have H2 gas plus O2 gas, okay, and let's say I've got some little equilibrium thing happening here, and I'm going to make water, vapor, gas, okay, and I've got my balanced equation, all right? So on the left-hand side of the equation, I have a total of 3 moles. On the right-hand side, I have a total of 2 moles. Okay, when I'm looking at my products and reactants. So if I'm looking at the concept of number of moles, if I increase the pressure, it's going to go to the side with the fewest moles of gas. It's got to be gas in these cases when we're dealing with pressure. If I decrease pressure, it's going to shift the equilibrium to the side with the most moles of gas. Okay, so in my water vapor example here, if I increase the pressure for this particular example, so if I increase the pressure, the equilibrium is going to shift to the right in this case because I have 2 moles on the right. It's going to go to the fewer number of moles. They take up less space. If I decrease the pressure, again, just for this example, the equilibrium is going to shift to the left in order to kind of spread out. You know, it can take up more space because there's less pressure on it. So that's the idea with Le Châtelier and pressure. Now, with changes in temperature, it works pretty much exactly the same way. Okay. So with this one here, okay, heat is on the reactant side. Okay, I can tell because this here, they put ice on that side. Okay, so they're removing heat. So with an endo and an exothermic reaction, essentially, if you just treat temperature like concentration, it works out. So if heat is on the reactant side and I add in more heat, okay, it's going to shift to the right. If I reduce the heat, it'll shift to the left. Now that's if heat is a reactant. Okay, and if heat's a reactant, it is endothermic because you are putting heat in. Okay. If heat is a product, so sometimes it'll say heat, sometimes they may say 150 kilojoules. They'll give you some value like we were just seeing in our thermal chapter. Sometimes they might just tell you that it is exothermic and therefore you should know heat's a product. And so if it's exothermic and I add heat, it's going to shift to the left. And if I decrease the heat, okay, it's going to shift to the right. So that's the idea behind temperature. Okay, it works pretty much the same exact way of concentration. If I add it, it's going to want to compensate it for it and use it up. Now, catalysts will increase the rate of both the forward and the reverse reactions. And I believe we talked about that in Unit 4 when we talked about kinetics, okay? Because here I have my activation energy, okay? So this is my activation energy of the forward reaction and my activation energy of my reverse reaction. But here my green line is my catalyst, is right there in the green line. So you can see the hill is shortened for both my reactants and my products. So it works in both ways with catalyst. And like I said, that's pretty much a review point for us at this point. So, you know, just what we deal with in terms of equilibrium, we still get equilibrium. Gets there faster, but our actual mixture of equilibrium is the same. We're still going to get the same amount of reactants and products. It's just the catalyst helps us get us there faster. Okay. So that's kind of the first section there. That corresponds to 6B in your reading. Now, this section here corresponds to 6A in the reading. So it's I like to present it a little bit out of order because I think learning about Le Châtelier's principle helps a lot. And it's also something you were probably exposed to in first year chemistry, so it's familiar to you. Now, the equilibrium constant, we've talked about a little bit. We talked about it in kinetics here. In fact, this is your rate law for this reaction. So the rate equals K forward times the concentration of the N2O4, the dinitrogen tetraoxide. Okay, if we're looking at the reverse reaction, okay, there's our rate law. Remember, this coefficient corresponds to that squared value right there. So I showed you this briefly before. The rate of the forward reaction is equal to the rate of the reverse reaction. Therefore, we can actually set these two equal to each other. And we had to do this when we had a fast initial step and a slow second step when we were at Unit 4. And we had to solve for the intermediate. So this is that same exact idea. So here, all we've done is simplify the terms, put the KF over the KR. But then we take it one step further and just simplify that KF and KR into a single constant, KEQ. And notice at this point now, the K is capitalized instead of those lowercase k's that we were using in Unit 4. Now, you're going to see a lot of K's in the next few weeks. Sometimes we just go for a generic K. There's KEQ, which is the equilibrium constant. There's KC, which involves concentration. KP, which is pressure. You're going to see both of those as part of this section. But then probably late this week, early next week, we're going to get to KW, which is for water. N acid, NB for base, and then there's SP for solubility product. And I think I'm leaving a K out, but you can see there's a lot of different Ks. And really all it comes down to is they're all an equilibrium constant. We're maybe just being a little specific and saying, oh, this one happens to be for concentration and that one happens to be for pressure. So it becomes really simple to write these equilibrium expressions. So we have this generalized reaction here, and it's really products over reactants. Okay, so products over reactants. That's very much like when we were doing products minus reactants. In fact, it actually mathematically works out the same way, but I'm not going to get into it there. Now, notice we use the coefficients. Okay, so these are the coefficients from the balanced equation, and those get raised to, those are our powers for our concentrations. Very important also, square brackets. Square brackets are an abbreviation for concentration, meaning molarity. Okay, and in fact, notice right here, I gave us a Kc, so that means I am talking about an equilibrium constant for concentration. Now, when we write these equilibrium constants, we are always going to exclude solids and liquids. This is huge, okay? That's a really important point to memorize. And I mean, it'll become second nature to you because we're going to do a lot of these. So really, equilibrium constants are only written for aqueous and gases. Okay, our pressures and our concentrations. And there's a big long reason why we don't include solids and liquids, but I'm not going to hassle you with that now. All you need to know is we don't include them. Okay. So we have this concept of heterogeneous equilibrium. And so heterogeneous means different. All right. And we also have homogeneous equilibrium, which is going to be same all the way throughout. And I'll show you what I mean. It really comes down to the states that the products and the reactants are in. So here's a short explanation about why we can leave off solids and liquids. But it's essentially saying that they don't change as long as they're at the same temperature. And usually in an equilibrium problem, you're going to be given a temperature, but you don't necessarily need the temperature to solve the problem. They're just telling you what it's at. So this here is an example of a heterogeneous equilibrium. I know it's heterogeneous because I have solid, aqueous, aqueous. I do products over reactants. Okay, so here's my products, my lead ions, and then my Cl ions, and then notice my coefficient of 2, it is raised to that power. So I have no denominator in this case because my PbCl2 is a solid, so I would exclude it. So like I said, this is an example of a heterogeneous equilibrium. I could actually write this the reverse way, because, you know, double-sided arrows there. And if I were to write my equilibrium expression, I would have Kc equals, well, this PbCl2, it's a solid, so it would be 1 over my concentration of Pb plus 2 over my concentration of Cl minus, and then the 2. So, you know, mathematically, they're actually going to work out the same, and we'll see that over the next few days as we do calculations. So even though I reverse the reaction, the Kc is going to come out to be equivalent. But just know that you can have no numerator and no denominator depending on the type of equation that you are given to solve. So take a moment, pause right here, and I want you to try and write the equilibrium expressions. And then when you're done, unpause and we can check those answers. Okay. So for this first one, products over reactants. So if I want to write these as a Kc, I would do Kc equals square brackets CO2 squared. Okay, I skipped the Sn because it's a solid. Divided by, I'm going to skip this because that's a solid, CO square brackets squared. Okay, because of this coefficient of 2 right here. Okay, for the second one, solid, solid, I can leave those out. I do products over reactants. Therefore, my CO2 is going to come first, concentration of CO2, just like that. Okay. And then lastly, for this one, same thing, solids, solids, Kc is equal to products over my reactants, Cu plus 2. You've got to have the square brackets. You have to have the ion charges if they're there, because this Zn solid is different than this zinc ion as an aqueous solution. Okay? So writing equilibrium expressions, pretty simple. Now, we can do the same thing for pressure. So a few moments ago, I mentioned that there is a Kp. The P stands for pressure. And we can deal with gases in a closed system. You're going to be dealing with a lot of partial pressures. You're going to be playing around a lot with PV equals nRT when we start solving these mathematically. So it's the same thing. It's products over reactants, except for now we use pressure and then we put the gas down there as the subscript. And then same thing here, the superscript is the coefficient from the balanced equation. So I believe, did I do one of these? Okay, no. So if I back up to the last slide and let me clear this ink. Erase all ink on slide. Okay, and let's say I wanted to do it for this top one and write a Kp. Again, I ignore solids and I would say Kp pressure is equal to the pressure of CO2 parentheses squared divided by the pressure of CO parentheses squared. Okay, so that's how I would write a Kp expression. You know, my second one here would be Kp is equal to the pressure of CO2. That's it. You could put parentheses around it for this particular one. It's not necessary because we don't have a power, we don't have a squaring or anything else it's multiplying against. Okay? So that's how you would write a Kp expression. It's just the difference is you would say P for pressure there. So Kc and Kp do relate. Okay, I said on the last slide you're going to be playing with PV equals nRT a lot. Okay, now a lot of these have to do with the the temperature that you're dealing with, and also the number of moles. So it used to be on the AP test, you had to solve for between Kp and Kc. Like they'd give you Kc and they'd ask you for Kp and vice versa. This equation is no longer provided on the equation page. So I'm not going to be testing on it, and I'm not really going to emphasize us solving it. There's still some practice problems that have it in there, and your reading still goes into it, because I think it's good for you to know that these two can be related, but we're really not going to focus on solving for it. Okay? So, you know, like I said, I'm going to skip these problems for now, and it's something we can certainly go back to for it. Now, one of the things I said was equilibrium can be reached from either direction. So I can come at it from my nitrogen dioxide or my dinitrogen tetraoxide. And so this is almost kind of like our rate experiments that we did in Unit 4. And it doesn't matter. What this is saying here is I can start with absolutely no nitrogen dioxide or dinitrogen tetraoxide, and I can put in 0.02 nitrogen dioxide and look at my products and reactants and look at my Kc. Okay. Here in experiment 4, all I did was flip the amounts. Okay. Now I didn't start with any nitrogen dioxide, and I started with the dinitrogen tetraoxide. Okay. And look, I still get the same Kc amount. Did these amounts come out to the same? Not quite. Okay. But it has to do with the relationship with this squaring right here. But notice the Kc always comes out to be exactly the same. Okay. So the key to this is it's the constant temperature. A K is only good for a certain temperature. And that is a really important point to know for the AP exam, because if you change the temperature, you're going to change the value of the equilibrium constant. Right? Now, they're not really going to have you do that too much. Okay, so it's not like they're going to give you experiment at one temperature and experiment at another temperature, except for maybe just a comment on them, like, hey, the Ks will be different. Something along those lines. Or in terms of Le Chatelier's principle, if I raise the temperature, what's going to happen to it? Okay, so that's the only way they would mess around with the temperatures on you. Otherwise, it's just going to give you a temperature in the problem so you know, hey, that's what it is for the K. Okay. So here, it's just showing you graphically experiments 3 and 4, and that we are coming to the same amounts. And same thing with the Haber process with the nitrogen and the hydrogen and the ammonia. Notice our concentrations are happening, at the same proportions there. So we touched on this a bit in our electrochemistry unit, and then again in Unit 5, our last unit on thermochemistry. And what does K mean? And so if K is greater than 1, it goes towards the products. Okay. You'll hear us also say it shifts to the right. Okay. And so it'll be product favored then at that point, because products are on the right-hand side of the arrow. Okay. If K is less than 1, the reaction is reactant favored, and you're going to have more reactants at equilibriums. Okay. And again, we will say for this one, it'll shift to the left. All right. For K is equaling less than 1. And so K is greater than 1, K is less than 1. And then, of course, if K is 0, the system will not shift. It is currently at equilibrium. And we'll see that when we start to calculate. Now, before we start to go full blown on the the Ks and the Qs, which is the second and third lesson, we just kind of want to deal with manipulating the equilibrium constants. So I showed you with that lead example that I could flip the equation and that it's going to flip this information. And so, if I flip my products and reactants, of course, it's going to be the inverse of the other one. And consequently, when I'm given the 1K value, if I flip it over and take the inverse, then I should take the inverse of the K. This is the same idea behind Hess's law. Okay, when you flip the one, you would flip the sign of the other. But in this case, instead of flipping the sign, you would flip the value. Now that 0.212 is underneath the 1. It's been flipped. Solve it mathematically. Okay, don't just leave it as 1 divided by 0.12. Actually calculate it out and get that value of 4.72 when you're taking the AP test. Okay. So those do show up periodically in multiple choice or as one part of a free response question. What do you do with the inverse? What happens when you multiply them by factors, which I'm going to show you on the next slide. Okay. So if we multiply it by a number, then the equilibrium constant is raised to the power of that number. So here with my dinitrogen tetraoxide, I doubled the amounts. So everything was raised by a factor of 2. So I'm going to take that and raise that by a factor of 2. And just like the other one, I don't know why I didn't calculate this out. You should go ahead and calculate out the 0.212 squared. If I were to multiply my equation by a factor of 3, and now I have 3 N2O4s, and then 6 NO2s, okay, then I would take my 0.212 and cube it, because it's, again, a factor of 3. And again, we could go through the mathematical support of proving this, how this works with Hess's law that we've studied. But at this point, there's no need, because really we're just trying to master the concepts for the AP exam. Okay, now if we are adding and subtracting reactions, okay, so if we are adding reactions just like the Hess's law, okay, then you would multiply the equilibrium constant. So if I had A makes B and I had C makes D, okay, and let's say my K for this value is 2 and my K for this value is 4. Okay, if I were to add these two reactions, so now I have A plus C makes B plus D, okay, it's telling me my K is now equal to 2 times 4, which is 8. So when I add my reactions, I multiply my equilibrium constants, my Ks. So this concludes the first section of notes. On Monday, I'll take questions or the next day that we meet, and then dive into the second section, which is a lot more mathematical and involves breaking down the problems more. How do we get those values for K when we're given different concentrations and pressures? So that's what we'll spend our time with then.